Hello everyone, and welcome to Linux Forensics here at Pentester Academy. In this video, we're going to show you how you can cat out files or print out files based on their inode number. And what we're trying to accomplish here is we're actually working our way toward being able to do directory listings for files that are stored inside of an image and do some other things with the files. We learned about directories in a previous video, and now we're going to apply some of that and extend our Python scripts yet again in order to be able to cat out a file associated with an inode. So what are we doing? Well, we've added to our xfs.py file. So here's our inode class, and I've added a couple of functions. So the first function I've added allows you to get a data block where you give it an image file name, an offset, where your file system starts, and then a block number, and optionally your block size if you don't have a standard 4K block. I will then seek to the appropriate place and return your block. Another function will return a list of data blocks. If you're using extents, I will use extents to give you the list. And in the case of using extents, we talked about these in a previous video, it is the most common case that you have a single level of the tree. So I have a little bit of a short circuit in this because I have to access the disk in order to get the list of blocks. That's why I had to define a method to read a block in. So here I take an inode object, and I also take an image file name, offset, block size, again optionally. I will take this, I create an empty list for my data blocks, and I say, are we using extents? If we are, the extents member for the inode object will return true, which means this list is not empty. And then I check and say, is the depth 0? That's the most common. If it is, I have typically up to 4 entries. And I say for I in the range of 1 to the number of entries plus 1, please go ahead and read this information. So I have a starting point, and I have a length. So I add to my starting block my length. Now, you might object and you might say, but I really wanted to have the length minus 1. That's what I should be adding. And you would be correct. However, because the range in Python is not inclusive of this final member, it will range from SB to EB minus 1. It seemed kind of silly to subtract 1 here only to add it back in the next line, so I didn't bother. And here I will just append whatever is stored in these extents into my list of data blocks. If in fact I have multiple levels to my tree, I have a pretty simple little while loop here. And I parse through the whole tree. And if you look at this code, what you'll see is that I'm checking to see, is this a leaf node? Is the level at 0 for this? Recall that every extent list starts with a header. And if the depth is 0, that means that everything that follows is a leaf node. So I parse the entire tree. And every time I find a leaf node, I add it. So I add it to my current level, and I start at 1, and I go to the end. And then I advance. I say current level is equal to my next level. So I'm loading this list. Now, once I'm done, I could do something really complicated where I say, okay, let's look at the logical block number, and we know that this one starts at 0 and then it's this length, so the next one should be here. Or I could do something super easy, which is what I chose, of course. I sorted my list, and that's what this construct does here. I said, I want to sort this. My sorting key equals lambda x dot block. So this says, please sort this based on the block. And then I will go through my list. I will do something very similar to what I did for the simple case. I have a little for loop, and I append all the data blocks to my list. Otherwise, I have old school blocks. Recall that the first 12 blocks are what we call direct blocks. I add those to my list. If I have more than 12 blocks, I have indirect blocks. I read in the indirect blocks, and then I iterate over those pointers. And since it takes 4 bytes per pointer, my block size, which is normally 4K, divided by 4, determines how many entries I have. So for each entry, I get the 32-bit value at the offset I times 4, and I say, is it 0? If it's 0, I call break, which gets me out of this for loop. Otherwise, I append it to my list. And I do something similar for the double indirect blocks. I've just added another level for my for loops. And once again, I do something very similar for my triply indirect blocks if I have some extremely large files. And it will go through this and add all of these block numbers to my list. And that's pretty much that. I've defined a new program called icat.py. What does it do? It takes an image file, an offset, and an inode number, and it displays the file for that inode. What I do is somewhat similar to my istat program. I create an extended metadata object. I find my inode. I load that inode into an object. Then I get my block list from that inode and image. argv1 is my image file. argv2 is my offset. And using the superblock size from my extended metadata object. And for each data block in my list, I call sysstandard_out_write. So I cat it to the screen, and that's pretty much it. And I use my standard trick, if _name, == =main, _, then I call main. So let's go ahead and run this real quick. So I will run it, and here I'm going to run it on inode 2, which you might recall is the root directory. I'm going to pipe it to xxd and pipe that to more. So here is my directory. You'll notice certain things that look familiar, such as lost and found, etc., etc. In a future video, we will decode all of this. I can also print out some inodes associated with my rootkit. Recall that this was one of them, 657,103. I pipe it to xxd and then pipe that to more. When I do so, I get something like this. It's an ELF file, and I will see some embedded strings. And this is, in fact, my rootkit. You can see Xingxi and other telltale strings. Well, that's all for this video. As always, if you're enjoying these videos here at Pentester Academy, please tell a friend.